Bayes Theorem. Welcome, everyone. Today, we are moving into a very exciting part of our probability unit. In our previous lessons, we spent some time exploring the concept of reverse probability and mastering the theorem of total probability. You'll remember that those tools helped us understand how to look at outcomes from a different perspective. Now, we are going to take those two fundamental ideas and combine them into a single, formal mathematical framework known as Bayes' theorem. This isn't just another formula to memorize. It is actually one of the most powerful tools in all of probability theory. The reason it's so significant is that it gives us a way to update our beliefs. It allows us to take an initial assumption about a cause and refine it by incorporating new evidence, specifically after an event has already taken place. As we move through the next few slides, we'll look at how this logic works and how you can apply it to solve complex real-world problems. Understanding the concept. Think back to the standard conditional probability we've studied previously. In those problems, we usually follow a forward-moving logic. We start with a known cause and ask, given that this specific cause has been chosen, what is the probability of a certain outcome happening? It's a direct, one-way street. However, Bayes' theorem is special because it flips this logic entirely. It allows us to work backward. It asks the much more interesting question. Given that we have already observed a certain outcome, what is the probability that it was produced by a specific source? We are essentially looking at the effect and trying to deduce the cause. But to use this mathematical flip, we can't just pick any random events. We need two specific ingredients in place. First, we need what we call a partition of the sample space. This is a collection of events, which we can label as E sub 1, E sub 2, all the way up to E sub n. For this to be a true partition, these events must be mutually exclusive, meaning they can't happen at the same time, and they must be exhaustive, meaning they cover every single possibility in our sample space. Second, we need an event A. This is the specific outcome or the effect we are interested in. Crucially, this event A must be something that can potentially happen under any of the conditions we listed in our partition. Now that we've introduced the name of our topic, let's really dive into the core concept of what makes Bayes' theorem so unique. Once we have these two pieces, our set of possible causes and our observed event, we are ready to move on to the mathematical formula that ties them all together. The mathematical formula. Now that we understand the logic of flipping the probability, let's look at the actual mathematical formula that makes this possible. Suppose we have a set of events, E sub 1, E sub 2, all the way up to E sub n, which, as we mentioned in the previous slide, form a partition of our sample space, as this just means these events cover all possibilities and don't overlap. If we have an event A that has a non-zero probability, we can calculate the probability of a specific hypothesis, E sub I, occurring given that event A has already happened. The formula is written as P of E sub I given A equals the probability of E sub I multiplied by the probability of a given E sub I, all divided by the sum, from j equals 1 to n, of the probability of E sub j multiplied by the probability of a given E sub j. I know that looks a bit intimidating at first, so let's break it down into two manageable parts. First, let's look at the numerator. The probability of E sub I multiplied by the probability of a given E sub I. Think of this as the probability of one specific path. It represents the chance that our chosen hypothesis, E sub I, occurs and that it leads directly to the outcome A. Next, we have the denominator. The summation from j equals 1 to n of the probability of E sub j, multiplied by the probability of a given E sub j. You might recognize this from our earlier lessons. This is the theorem of total probability. This part of the formula calculates the sum of every possible path that could lead to event A by dividing our specific path by this total sum. We are essentially normalizing the result. This ensures our final answer is a proper probability that accounts for all possible causes. In the next slide, I will show you a step-by-step guide on how to organize these pieces when you're solving a problem. Step-by-step application. Now that we have seen the mathematical formula and how it's structured, you might be wondering, how do I actually approach a word problem without getting lost in the notation? Well, I recommend following a consistent, logical workflow. First, you need to identify the partition. This means you look at the problem and define your possible causes, which we label as E sub 1, E sub 2, all the way up to E sub n. Remember, these must be mutually exclusive, meaning they can't happen at the same time. Second, identify the observed event. This is your event A. Think of this as the effect or the outcome that has already been observed to have happened. Third, list the knowns. Before you start calculating, explicitly write down the probabilities of your causes, which is P of E sub I, and the conditional probabilities, which is P of a given E sub I. Having these written out clearly prevents simple clerical errors. Fourth, calculate the total probability. You need to find the total probability of event A, written as P of A. To do this, you'll use the theorem of total probability, which is the sum from j equals 1 to n of P of E sub j times P of a given E sub j. Essentially, you are summing up all the different paths that could lead to event A. Finally, apply Bayes' formula. This is the final step where you take the probability of the specific path you are interested in, the numerator we discussed in the previous slide, and divide it by that total probability you just calculated. If you follow these steps systematically, you'll find that even the most complex problems become much more manageable. Let's put this exact workflow into practice with a real-world example involving factory quality control. Real-world example: quality control in a factory. Now that we have understood the theory and the formula, let's put everything into practice with a real-world scenario. Imagine a factory that uses 3 different machines, Machine 1, Machine 2, and Machine 3, to produce the same type of light bulbs. We know that Machine 1 handles 50% of the total production, but 3% of its bulbs are defective. Machine 2 produces 30% of the bulbs, with a 4% defect rate. Finally, Machine 3 produces the remaining 20%, and 5% of its bulbs are defective. Here is our problem. Suppose we pick a bulb at random from the finished stock, and upon inspection, we find that it is defective. Our goal is to use Bayes' theorem to find the probability that this specific defective bulb was produced by Machine 1. Let's walk through the solution step by step, following the logical framework we discussed in the previous slides. Step 1, we need to define our partition, which represents our possible causes. Let's denote the event that a bulb comes from Machine 1 as E1, Machine 2 as E2, and Machine 3 as E3. From the problem, we can write down our prior probabilities. The probability of E1 is 0.50, the probability of E2 is 0.30, and the probability of E3 is 0.20. Notice that these sum up to 1, meaning they cover all possibilities. Step 2, next, we identify the observed event or the effect. Let's call event the event that the bulb is defective. Step 3, now we list the conditional probabilities. These are the probabilities of the effect occurring, given a specific cause. So, the probability of a given E1 is 0.03, the probability of a given E2 is 0.04, and the probability of a given E3 is 0.05. Step 4, before we can find our final answer, we must calculate the total probability of event occurring. This is where we use the theorem of total probability that we learned earlier. We sum up all the different paths that lead to a defective bulb. That is, the probability of E1 times the probability of a given E1, plus the probability of E2 times the probability of a given E2, plus the probability of E3 times the probability of a given E3. When we calculate this, we get 0.015, plus 0.012, plus 0.010, which gives us a total probability of 0.037. Step 5. Finally, we apply Bayes' theorem to find the probability of our specific hypothesis. We want to find the probability of E1, given that event A has occurred. To do this, we take the probability of the specific path for Machine 1, which is the probability of E1 times the probability of a given E1, and divide it by the total probability we just calculated. So, we take 0.015 and divide it by 0.037. This gives us approximately 0.4054. To conclude our analysis, we can say there is approximately a 40.54% chance that the defective bulb we found was produced by machine 1. As we move to the next slide, keep in mind how this process allowed us to update our initial belief about machine 1's contribution once we had the new evidence of the defect. Key takeaways. First, I want you to remember the concept of reverse logic. Throughout this lesson, we've seen how standard probability looks at a cause and predicts an outcome, but Bayes' theorem flips that script. It allows us to work backward, moving from the observed effect back to the original cause. Second, think of this theorem as a tool for updating probability. We start with what we call the prior probability, which is the initial probability of an event, written as the probability of E sub I once we observe new evidence. Represented by event A, we can calculate the posterior probability, which is the probability of E sub I given A. It's essentially the process of refining our initial beliefs based on new data. Finally, if you ever feel overwhelmed by the complex-looking formula we saw on slide 3, just remember its underlying structure. At its heart, the formula is simply the probability of one specific path divided by the sum of the probabilities of all possible paths. All right, let's wrap up our session by summarizing the key takeaways from today's lesson on Bayes' theorem. Now, before you move on to your practice problems, let's take a moment to look at some common pitfalls where students often lose marks, so you can approach your exam with confidence. Common mistakes to avoid. First, the most frequent mistake I see is confusing the probability of a given E sub I with the probability of E sub I given A. It sounds subtle, but it is a massive difference. Remember, the probability of a given E sub I represents the probability of the effect occurring, given that a specific cause has already happened. This is usually the information provided to you in the problem statement. On the other hand, the probability of E sub I given A is what we are actually trying to find, the probability that a specific cause was responsible now that we have observed the effect. Always ask yourself, am I looking for the cause, or am I looking at the outcome? Second, watch out for forgetting the denominator. It is very common to do all the hard work of calculating the numerator, the probability of that one specific path, but then forget to divide by the total probability of A without that denominator. Your answer isn't a properly normalized probability. As we saw in our factory example, the denominator is the sum of all possible paths, and you must include every single one to get the correct result. Finally, be careful with incorrect partitioning. When you are defining your events, E sub 1, E sub 2, and so on, you must ensure they are both mutually exclusive and exhaustive. This means that no two causes can happen at the same time, and together, they must cover every single possibility, meaning their probabilities must sum up to exactly 1. If your partitions are incomplete or overlapping, the entire framework of the theorem breaks down. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even students who understand the logic of Bayes' theorem can lose marks by making these specific errors, so please pay close attention. Keep these 3 points in mind, and you will be well on your way to mastering Bayes' theorem.